a marketing manager here at SOR. In this video, I'm going to show you how to configure a 2700 series ultrasonic level switch with a single point probe. Each 2700 series ultrasonic level switch consists of two parts, the electronics and the probe. Both the electronics and the probe have their own unique model numbers. The electronics will begin with 2700, whereas the probes will start with either 371 or 372. The 371 is indicating that it is a single point probe as seen here, with this style being the N or notch type. Here I have a 372 or a dual point probe, also with the N or notch style of cavity. When ordered from the factory as a complete unit, the device will arrive already assembled. However, if you're ordering a replacement electronics or probe for an existing unit, those will need to be assembled in the field. To start, remove the housing cover. Start by removing the screws located here, here, and here on the interface board. After the screws have been removed, the interface board can be removed. It is an assembly of two boards with the interface board on top and the power board below. On the power board are three connection points labeled B, A, and T. These three connectors are where the probe cable connections will connect to. For single units, only points A and T are used. Each probe will have the connectors labeled with their corresponding locations of A, B, and T. Plug those into the back side of the board. So here we have A connected to A and T connected to T. With the cables connected to the back of the power board, reassemble the interface board into electronics housing. Now that everything's assembled, we are ready to proceed. At the top of each interface board is an 11-position terminal strip. Labels are printed directly onto the interface board. Here, these three correspond to gap A. These three correspond to gap B. Do note that single point units will not use gap B. Next, these three are for our fault relay, and these last two are for power. Unscrew the terminals and provide power to the device. Note, ensure that you are providing the correct power based on what is shown on the nameplate rating. And now with our power wired, we are ready to boot up the device. Before we dive into configuring specific features, let's take a closer look at the interface board and review the different features and LEDs and what they represent. Starting with the features, on the left here we have the Field-Selectable Failsafe switch. It is a two-position switch that can be toggled left or right. Next, we have the self-test button seen here. In the middle, seen here, is our time delay dial, and to the right of that is our calibrate button. Now let's look at the LEDs. Starting with the LEDs below the terminal strip. Up first, we have the wet and dry LEDs for each gap. The wet LED is blue and indicates if there is liquid present in the cavity. The dry LED is amber and indicates if there is an absence of liquid in the cavity. The same colors are used here for gap B, though those will only be seen on dual point units. Next up we have the fault relay, this single red LED here. If this is on, this indicates a fault. And then lastly we have the power LED here, lit green, indicating that the correct amount of power is being supplied to the device. The next set of three LEDs are to the left of the self-test button seen here. During normal operation, these LEDs will be off and they will only become lit during the self-test procedure. We'll reveal those in further during the self-test section. The last two LEDs here are for pump logic, which only applies to dual point units. Since this is a single point unit, we'll ignore the pump logic LEDs and move on to the next section. Normal operation. When the device operates, it detects if there is liquid present in the gap. This change can be seen with the LEDs in either the gap A and or the gap B. Right now it is empty, but we're going to insert it into this water column. We can see here, as it's inserted and liquid fills the gap, it changes from wet to dry. The first feature we have is the Field-Selectable Failsafe switch, seen here. It is a 2-position switch, with it in the left position labeled here as low, and to the right here labeled high. Units that ship from the factory will have it in the high position by default. This can be changed into the low position, and it will reverse the actuation of the device. Please refer to the continuity charts on page 10 to see how they will behave based on the position of the failsafe switch. For the next feature, we have the time delay dial, seen here. Each 2700 series comes with an adjustable time delay. It's an integral timer that starts when liquid level is either detected in or removed from the sensor cavity. The dial can be turned from here, pointing in the lower left corner clockwise down to the lower right corner. There are labels around the outside of the interface labeled 0, 5, 10, 15, 20, 25, and 30 seconds. With the dial turned all the way in the clockwise direction, it will be at 30 seconds. Turning it in the counterclockwise direction to 0 turns the time delay off. Next, let's demonstrate the time delay feature. Currently I have it set to the 0 or off position. When I lower the probe into the water, it will actuate immediately. Removing it and will deactuate immediately. If I turn the time delay somewhere to the middle here, around 5 to 10, 15 seconds, and now I put it in the water again, we will see when it detects liquid in the gap as the LED will begin flashing. Seen here. While the LED is flashing, the time delay is active. Once our time delay timer is finished, after about 10 seconds, the device will actuate and stay in the actuated state. The same can be seen when we remove it. The amber dry LED will begin flashing and remain flashing during the duration until the time delay is complete. At that point, it will deactuate. Next, we'll review the self-test button, seen here. A self-test button comes standard in all units and is used to manually change the state of the relays to ensure that it is properly connected back to the control system. It also performs a check for continuity between the electronics and the probe to ensure that they are connected and that the transmit and receive crystals are working properly. Upon pressing the self-test button, the middle LED labeled A here will light up amber, indicating that the self-test has begun. If the test passes, the top LED with the P label will flash green, and if there's a failure, the bottom F will light up red. Everything is connected properly, so we'll get a pass result here. I'm going to press it, and now we'll see our green light indicating that it passed the self-test. Next, let's demonstrate what it looks like when it doesn't pass the self-test. Now let's show what happens when the self-test button is pressed and the device, the electronics, and the probe are not properly connected. In this case, I have both the A and the T cables disconnected from the back of my board. Within the GIs, there's a table that lists the priority of symptoms and how they will appear. In this case, with the T cable disconnected, we'll see the gap A wet LED up here flashing, and then the fault LED here flashing red. When I press the self-test button, we'll see that occur. It's flashing red, indicating there's a fault state, and these here are flashing. This indicates the T cable is disconnected. Turn off power to the device. Let's now go and plug the T connector into the back of the board. After restoring power to the device, it will go back into its normal operating state. When we press the self-test button again this time, it will now show us the second failure, that being the A cable disconnected. This will be seen as flashing dry LEDs and the red fault LED flashing. Let's correct this. Let's turn off power to the device, undo our interface board, turn it back over to the power board, and now let's plug in this A cable to the A connector. Now that the probe has been properly reassembled back to the electronics, let's power up the device and do the self-test button one last time. The device powers up and now it's in the normal operating mode. We press self-test and we'll see it will give the green passing LED result. The device is now operational and ready to use. Now, let's look at the fault states that could occur. You will know a fault state has occurred when, upon powering up the device, the red fault LED is lit. Each fault state requires a different type of calibration to correct. Next, let's perform the 3 different calibrations that may be required to the device. First, we're going to start with the sensorless calibration. Now, let's take a look at what the device will indicate when a sensorless calibration is required. When we turn on power to the device, the LEDs will begin flashing to indicate the fault that is occurring. Here we see both the gap A and gap B, wet and dry LEDs are flashing repeatedly, with the fault relay LED on and the power relay LED on. If we look here in the table of troubleshooting, we can see here that this is an indication that a sensorless calibration is required. To perform the sensorless calibration procedure, we'll start by turning off power to the device. Ensure that the sensor is completely disconnected from electronics. To do that, we'll remove our 3 screws, gently pull out the interface board, and disconnect the sensor cables from the back of our power board. And turn the device back on. Let's start and perform the sensorless calibration procedure. Press and hold the calibrate button for approximately 3 seconds. Afterwards, all the LEDs will begin flashing. When you let go, it is in the calibration selection mode, with the sensorless calibration selected, seen here by these LEDs flashing. Note, after 10 seconds of inactivity, it will leave the calibration state and return, seen here, back to the normal operation. So, once we're in that calibration selection mode, we're going to press and hold calibrate to begin. So, let's do that. Let's go back into the calibration selection. We're now in selection with the sensorless calibration selected, so let's initiate it. We're going to press and hold the calibrate button again for about 3 seconds. All of the LEDs will begin flashing. Now it can be released. At this point, the device will proceed through the sensorless calibration procedure without requiring additional input from the user. This will be seen by the gap A-B wet and dry LEDs flashing rapidly, but their speed and frequency will decrease as it gets towards the end of the calibration. As the calibration is finishing up, we will see them flash rapidly 5 times, like what's being seen here, and then they'll flash on and off for 1 second, indicating that the sensorless calibration is now complete. However, we still see that there is a fault LED on, with the 2 dry LEDs flashing. This is an indication that a now dry calibration is required. Next, let's perform the dry sensor calibration. To start, remove power from the device. Remove the 3 screws and gently disassemble and remove the interface and power board. Ensure that the probe connectors are connected to the back of the board, with the correct cables going to the correct connectors with the labels. Now that we've reconnected the probe to the power board, we'll put it back inside the electronics housing. Now, let's perform the dry calibration procedure. We'll restore power to the device, and we'll see that it's still indicating that a dry calibration is required by the dry LEDs flashing, our red and green LEDs lit. Press and hold the calibrate button again. After 3 seconds, the LEDs will begin flashing rapidly. This is an indication you can let it go, and we're in the selection mode. Currently, the sensorless is selected. Pressing calibrate button once will now change that only our dry LEDs are flashing. This means we can continue with the dry calibration. Press and hold the button for approximately 3 seconds. When the lights begin flashing again, it can be released, and now the calibration will proceed without further input from the user. Our dry calibration is now complete. We can see though that we still have a fault indicated here, and we can see that it is now our wet LEDs that are flashing. This is an indication that a wet calibration is now required. Last, let's perform the wet calibration procedure. Start by removing the interface board and checking that the sensor is connected to the proper connection points on the back of our power board. Reassemble the boards back into the housing. First, we will submerge our probe into our process media, here being liquid water. Apply power to the device. The device will boot up in the normal operating state. To do a wet calibration, start by pressing and holding the calibrate button for 3 seconds. After 3 seconds, the lights will begin flashing rapidly. This indicates we're in the calibration selection mode. With the sensorless calibration selected, pressing calibrate button once will turn us to the dry calibration, and then pressing it one more time will put us in the wet calibration selected. Press and hold the calibrate button for 3 seconds now to initiate the wet calibration procedure. Once the lights begin flashing, it can be released, and the device will proceed to do the wet calibration without further input from the user. The wet calibration is now complete.
And that covers everything needed to configure your single-point 2700 series ultrasonic level switch. The general instructions referenced in this video are available at sorinc.com, and there will also be links in the video description you can use to download them. I hope you enjoyed this demonstration, and thanks for watching.